So hi guys, we are at the day 11 of dynamic programming series, and the problem that we are going to discuss today is largest independent set. It is a short problem, but the concept that we are going to learn today is very crucial, that is DP on trees. So let us see what the problem is. Given a binary tree, find the largest independent set. We need to find the size of the largest independent set. So basically we are given a binary tree, हमें एक binary tree given है, and we need to find out the largest independent set in it. So first of all, what is a binary tree? Basically all of you might be knowing what a binary tree is, and for more clarity I will give you the exact definition. That is, a binary tree is a tree in which a node has at most two children. It can have 0, 1 and 2 children. So basically it is a binary tree, and we need to find the size of the largest independent set in it. So हमें largest independent set निकालना है. So what is largest independent set? Basically it is a subset of all the tree nodes in an independent set if there is no edge between the two nodes of the subset. So basically हमारे पास एक tree given है and there are multiple nodes in it, and we'll include a particular node in a set such that it does not have a direct edge between to another node in the given same set. So एक बार एक example के through let us clear it more with the help of an example. So basically ये एक binary tree given है हमारे पास. So we have multiple nodes in it, and we need to find the largest independent set. So one independent set could be, I'm not saying largest, one independent set could be 10, 40 and 60. So it could be one possible set because we can see that there is no direct edge to it. We have an edge from 10 to 20, and then we have an edge from 20 to 40, but we do not have a direct edge from 10 to 40 or 40 to 60. So in either of these three nodes we do not have a direct edge. We have a via edge through it. Means we have a via edge, like we have an edge from another node towards it, which is not included in this particular set. So this is a possible example of an independent set, but we need to find the largest independent set in it. So the length of the largest independent set could be 5. Let us see with the help of this example how it can be, like 10, 40, 70, 80 and 60. So we have considered all the possible nodes which do not have a direct edge, and the number of length of this particular set is 5. So what are the nodes in it? 10, 40, 70, 80 and 60. We can see in this given tree that they do not have a direct edge or any common edge connection between the two nodes. So that is the description of the problem, and we need to find the largest independent set size. We do not need to find the nodes, we only need to find the size of this particular largest independent set. So we have understood the problem. The next part of this video consists of the solution and how we can think about this problem. So there is a small request I would like to share with you guys, that please think of the solution and apply the methods that we followed up during this series, DP series. It is not a difficult problem, it is a very easy problem. So I would request you to kindly pause the video and think of a solution and write the solution in the given link that I have provided in the description for submission of the problem. So it will increase your mental ability, and it will increase your problem solving skills. So I would request you to kindly solve this problem by your own, and if you want to see the solution, then you can please continue the video. So what are the observations that we do? There are 3 steps that we usually follow in the DP series. First, we'll make the observations. हमें observations करनी होती हैं. Then second point is we'll develop a recursive solution. We'll get a recursive constraint that हमें एक recursive solution develop करना होता है to solve how we are solving this particular DP. What is the pattern that we are getting from the DP? And the third one is applying the dynamic programming and reducing the time complexity. So हम उसमें finally dynamic programming का addition करते हैं ताकि हमारी time complexity जो है वो recursive solution जो बन रहा है उसकी हम reduce कर सकें. So these are the 3 things that we generally follow while solving a DP problem. So let us see how we can do this. In this particular problem, it has been given that we cannot have 2 edges with 2 nodes with a common edge. So we cannot have 2 nodes with a common edge. So one thing is very clear, that if we include one node, that we cannot include its children. That means if we are taking one node, अगर हम एक node ले रहे हैं, then we cannot have its children in the largest independent set or in an independent set, because they'll have direct edges. If we are taking a particular node, then its children will be directly connected towards that node with a direct edge. So we cannot take the children if we are taking the particular node in it. So it is very clear from the given problem. This intuition is very clear. But we can include its grandchildren. If we are not including the children, we can include its grandchildren, because they are not connected directly towards the particular node. If we are including a particular node, then we cannot include its children, but we can include its grandchildren. So I'll clear this up with the help of the example that I gave to you. Like, this is a particular node that I am including in the given set. I will not include its children. These 20 and 30 are its children. I am not including these children, but I can include its grandchildren, that is 40 and 60. This is because they do not have a direct edge between this. They have a via edge via this particular node. They do not have a direct edge from this particular node. If I am including this particular node in the largest independent set, then I can include its grandchildren, but not its children. So these are the common observations that we can get through this problem. Now, what are the other observations that we can make? These are the perfect observations that we can make. Now, that is simple. If we include the node in the LIS, then we can include its grandchildren. First thing is very clear. Now the second thing is, otherwise we can include its children. So these are the two observations. That if we are including a particular node, then we can include its grandchildren towards it largest independent set, or what we can do is we'll include all of its children and do not include that particular node, and we'll include all its children only, not grandchildren, not that particular node, only its children. So these are the two options that are available to us. So this is the problem. We have broken the problem into some observations that we can get through this given constraints of the problem. So for a node x, what we can say is, हम क्या कह सकते हैं एक particular node x के लिए कि the largest independent set of a particular node x is the maximum of 1 plus sum of the LIS, the largest independent set of the grandchildren of x, comma sum of the largest independent set of the children of x. So what is this formula that we have developed is, one, why we are including one is the particular node. हम एक particular node के लिए decision ले रहे हैं कि अगर हम इस particular node को include करते हैं largest independent set में, if we include this particular node, then this particular node, of course it is one only, plus the sum of the LIS of grandchildren, and the LIS means the recursive call on its grandchildren, के what is the largest independent set forming from its grandchildren, LIS of its grandchildren of x, all the summation plus 1 this particular node, or comma sum of LIS of children of x and the children of x. The max of this we are making at LIS of x. So as we have discussed in the earlier part of the video, if we include a particular node, then we will include the grandchildren of that node. So this is the one part of this formula. Either what we can do is we can include all the children of that particular node, excluding the node and its grandchildren. So it is the second part of this formula. So the max of these will be the answer for this LIS of x, that is for any node x, the maximum of these two will be the answer. So I think it's very easy to think about this particular approach, and as we have solved many problems in the DP series, so I think this kind of intuition might be developing in the mind of all of you who are watching the video. So let's move to the next part. We can see that there are a lot of repetitive sub problems in this recursive solution. So we have developed the recursive solution. Now we are seeing that now we are on the third part of the problem. We have developed the observations, we have developed the recursive approach. Now we are on the third part, that how we'll apply the DP in this particular problem. So we can see there are a lot of repetitions. How? Like for example, we are computing the LIS of 10. So for 10 we are computing the LIS, and we'll need the grandchildren for that and children for that. So for grandchildren, let us suppose we have 40, 50, 60 and 70. So 50 is a grandchild of this 10 particular node 10. So we are including this as a grandchild, and we need to find the LIS of this for computing the LIS of this particular node. So we need to have the computation for this, and also for computing 20 we need to have the idea of children and grandchildren, and 50 is also a child of 20. So we need to know the LIS of 50 in both the cases. So while compute the LIS of 50 in both the cases, we can compute it one time and store the result and then return it to whenever it is asked for the next time. So this is how we can develop a DP in this. So in the recursive approach, while calling for LIS of 10, we are making the call for LIS of 50. And in the LIS of 20, we are making again a call to LIS of 50. So why calling LIS of 50 two times? We can call it for the one time and then store the result and then provide the solution to the next time whenever it is called. So this is how we need to develop the DP approach. Why to again and again call the same thing? Rather we can store it at a single point of time and then return it to whenever the particular thing is called next time. So this is the idea behind the DP. So let us see how we can do this in a particular DP approach for this particular problem. So this is the solution for this LIS. So we are given a root node at the initial level. So we have been given this particular root node, and if the root node is null, then we'll return 0 because there is no child and grandchild for this and it is already null. So what we'll do is we'll return 0 to it. And what is this root.lis? It is a particular thing that stored the LIS till now of the root. So basically we have components of this tree node is that we have left, we have right, we have data, which is the value at that particular node, and we have the LIS. So initially when we are developing a recursive solution, what we are doing is we are only getting three things, that is data, left and right at the structure of this particular node of the tree. But now what we are doing is when we are developing a dynamic programming solution, we are taking an extra constraint, that is LIS, which will store the LIS at that particular point. So if we have the value of LIS, that means if we have what we are getting LIS at that particular node, what we'll do is we'll simply return this. Rather than computing it all over again and again, we'll simply return this root.lis. So this is the part of root.lis. And if one thing is I want to say, that if you're not clear with what are the constraints of binary tree and how we develop a root node and all, first clear that and then approach this problem. So it is very important to clear the basics of the binary tree. So if you're not clear with this, so please clear the basics of the binary tree, and if you are clear with binary tree, then you can proceed towards the problem. So if root.left equals null and root.right equals null, that means it is the leaf node and both the values of left and right are null. So what we'll do is we'll make root.list, that means it is the leaf node, and root.list will be 1, and we'll return root.list. So we'll return this if it is a leaf node. Okay, now moving towards the other part of this particular code. So if LIS child, what we are storing in this LIS child is we are taking all the children. So we have two options, as we have discussed in the previous part, that what we'll do is either we'll include the particular node and its grandchildren, or what we can do is we'll include all its children. So in this particular variable LIS child, I am including all its children. I am making a recursive call on LIS of root.left plus LIS of root.right, and I am getting all of its children LIS in this particular variable. Now this is the second variable where I include the particular node and its grandchild. So I am initializing it with 1 because I am including the particular node, so it will be 1 plus all its grandchildren. So what I am doing is, if it has root.left, means if there is a left node at this particular node, then I'll include all its grandchildren. Left.left means its left grandchildren, and left.right means it's all left part right grandchildren. So I am including all its grandchildren at this particular position. And if this root has right, that means it has a right node. If it does not have a right node, then it cannot have a grandchildren. So if this root has a right, then I am including all the right grandchildren of root.right.left plus root.right.right. So these are the grandchildren. You can visualize this with the help of an example and with the help of a tree. So what I am doing in this particular case, so I included all the grandchildren LIS in this particular case, and I am making the recursive call on these grandchildrens, and then I am getting the answer finally. And I am getting the answer for this is LIS grandchildren in this particular variable. And at last what I'll do is I'll put the value of, because we are calculating for this particular root, so at this particular root we need to fill the LIS value. If the LIS value is not found in this particular case, then I'm computing the LIS value, and I'll compute this LIS value, and I'll make it as max of LIS of child and LIS of its grandchild. So we have calculated both LIS of child and LIS of grandchild. The max of this will be stored in the root.list, and at last what we'll do is we'll return the root.list, that we are getting the maximum at the particular node. And this is the whole answer for this particular problem. So I think if you know the basics of binary tree and you have continued studied till this problem, the DP series that I gave to you, so it will be quite easy problem for you to solve. But the concepts is very important for DP on trees and all. So it is that's it for day 11. and the concepts that we have learned today, I'll discuss it later. First of all, I would like to give you one task for you. So the task is, that is, in this particular problem, why we are not adding up the values at even and odd levels of the tree and returning the max of it. So the problem is, in this particular problem, why we are not taking the values at even and odd levels. So what I'm trying to say is that take a tree and then calculate all the LIS values at even and odd levels of that particular tree, and add all the values at particular even levels and add all the values at particular odd levels and return the max of it. So why we are not doing that? Why we are not trying to take this problem in a greedy approach? So I would like to hear what you guys say. So do comment your answer in the comment section, and let's see where the conceptual knowledge is proceeding towards this TP series. So concepts that we have learned today is DP in trees and memoization in trees. So we have learned two concepts, that is how we can store the results in trees. Like in struct of the tree, we can store a particular variable and can reuse the variable again and again. That is memoization in trees, and the dynamic programming in trees we have learned today. So if you have any doubts, you can always comment in the comment section, and you can send us your doubts in the email that we have provided in the description. You can follow us or get connected to us through the links that we have provided in the description, and try the problems. So please do like, share and subscribe the video. Thank you.